So I wanted to talk about graph connectivity. This is a fundamental property of graphs that has many applications. So for example, let's assume we had a network, and each edge represents that two machines are directly linked on the network. So here's a very simple graph, a very simple network, and I might want to know, is it possible for me to route messages from vertex U to, say, vertex V? And in this particular case, there isn't, because there's no way for me to get from U to V by traversing a sequence of edges. I can, say, route from U to, let's call this W, because I can traverse this edge and this edge and then this edge. So we'd say that U and W are connected and U and V are not connected. I'll make these notions more formal in a minute, but the simplest definition for connectivity is a path, and that's a sequence of edges that starts at some vertex and moves along adjacent vertices. So it's a pretty simple idea. So for example, let's say that I label this X and this Y. Then one example of a path would be U, X, Y, W. So U goes to X, goes to Y, goes to W. It's a valid path because these edges are connected via adjacent vertices, and we have an initial vertex U. So we went from, and the length here would be 1, 2, 3. This is length 3 because we traversed 3 edges, 1, 2, 3. Now if you wrote down U, Y, and then V, I would say this is not a valid path because, well, there's no way to get directly, U and Y are not adjacent, and then Y and V are not adjacent. So I would also say that U, Y, W is not a path, even though Y and W are adjacent. Again, I can't directly go from U to Y, they're not adjacent vertices. So just a few more notions. We have a circuit is a path that begins and ends at the same vertex. So for example, the path U, X, Y, X, U is a circuit. So we could go from U to X to Y to X and then back to U. Yes, we began and ended at U. We had a valid sequence of edges here, so it is a circuit. And we say that the circuit, so for example, if I added an edge here, then another circuit would be U, X, Y, U. Okay, so U to X to Y to U. And this circuit, the second one here, this is a simple circuit because it doesn't repeat any edges. So simple circuit, typically simple means no repeated edges. This first circuit here is not simple because it repeats, it goes U to X to Y to X to U, so it's repeating this edge right here. It's also repeating this edge, so it's repeating edges, so it's not simple. But this circuit, u, x, y, u, is simple. We also have the notion of a simple path. And that's just a path in the graph that doesn't repeat any edges. So for example, u, x, y, u to x to y, that's a simple path, but u, x, u is not a simple path, right? U goes to x and then back to u, that's not a simple path. And so you might have noticed that u, x, u is a circuit, right? It begins at u, it ends up at u, and it is a valid path. It has length 2, so u goes to x and then x goes to u. You only traverse 2 edges. So in this class, we're going to say that all circuits have length at least 3. We're not going to consider these sort of trivial circuits where you move from one vertex and then you move right back. We're only interested in circuits that have length at least 3. And one final bit of terminology, if a simple circuit with no repeated vertices we're going to call as a cycle. Okay, so for example, let me change this graph a little bit. So consider the following simple circuit. Let's see, U, X, A, B, X, Y, U. Okay, I went from U to X to A to B to X to Y to U. So notice I repeated the vertex X, but I didn't repeat any edges. I took this edge, these edges all the way, it's like an hourglass. So this is a simple circuit. But it's not a cycle because I repeated this vertex X. On the other hand, X, A, B, X, this would be a cycle because I didn't repeat any vertices, well, except for the very first and last vertex. In any circuit, the first and last vertex are always going to be repeated. And finally, and this could be the most important definition, we're going to say that a graph is connected if for every pair of vertices U and V, there is a path from U to V. So for example, in this graph here, you can see that this graph is not connected. Why? There's no path from U to V. In fact, this graph has 3 connected components. Here's one connected component, here's another connected component, and then here's this larger connected component. Within each connected component, every 2 pairs of vertices are connected. So for example, if you only look at the vertices of this graph here, of this subgraph, you'll see it's connected. For any 2 pair of vertices, you can get from one to the other. The same with this very small graph here. These are the only 2 vertices, and they're connected. And this subgraph here, with these 3 vertices, well, for any 2 vertices in this subgraph, they are connected. So you have 3 connected components. I'm not going to formally define what a connected component is, but you get the idea. And so if we were to just erase these two components, we'd be left with this particular graph. You know, if you pick any 2 vertices, say U and W, well, there's a path from U to W. A to Y, there's a path. So for any two vertices, just by looking at it, you can see for any two vertices you pick of this graph right here, you can get from one vertex to the other via a path, so the graph is connected.